Okay, good. All right. Yeah, we let's officially start the session today.
Okay.
We may use some 14 minutes in working out on the going over this section on ANOVA. ANOVA derived its name from analysis of variance, ANOVA, ANOVA. Although it says ANOVA, analysis of variance, but its goal is to test the differences of means. So if you only look at the analysis of variance, you may not think, oh, it has to do with means, but actually it's a how do you say, it's a kind of detour to get to get to a destination through detouring. We can just technically we don't have a way to directly compare the differences of the mean, so we have to compare the variances, and through the comparing the variances, we are able to make conclusions about the differences of the means. So this is something that we need to be clear. First of all, you know, we may not we don't have to remember all the formulas. That's not too important for me in a real sense. But as soon as we heard that ANOVA, we need to be able to tell people, oh, or I immediately you should click in us that it's about comparing the multiple means from the different populations. So, and with that, then we can move on to see the details in these sections. We should cover 10.1, 3, 4, and 5. Excuse me. Okay. The reason for skipping the 2 is so actually if you got that, we cover 10.1 already. Yeah, we need to be able to sum up with one sentence to tell people what ANOVA is all about, and that was according to just what I just described, to compare the multiple means to the analyzing the variance. Okay, so that's the introduction.
Hey, Professor.
Yeah.
This is Mike. Sorry, I have one quick question. Would you say that that ANOVA is really an extension of a t-test?
You may
in a way.
Yeah, you may say so. Yeah, you can say that because if you go to 10.2, you can you can see that if we can use ANOVA to test for the two treatments, that means 2 different means. But then it will become a special case of ANOVA, and it will be just the t-test.
Okay. Yeah. Is one option more powerful than the other, or should they both provide the same information as long as is one factor with 2 levels?
It's actually the same.
Okay.
Yeah, actually the same. If you go there and you will see, if you read this statement, and of course theoretically we can show here is in this section present the simplest form of ANOVA procedure, the case of studying the means of 2 populations 1 and 2. Comparing 2 means, the ANOVA will result in the same conclusions as a t-test and independent random variables.
Okay.
Yeah.
Got it.
Yeah, because when you have you can derive, and then you will be able to see that the ratio will be this when you only have two, this ratio actually should become f test. How do I say it? Yeah. Where is it? Yeah, it's using app test, but okay, yeah, you can follow this example and then see is although it used f f, but it should the result, at least the result should be the same as described there. But I remember the test statistics should also be able to be derived as a t, although it doesn't. Let me see. It is not surprising that in the previous example, the conclusion reached using the ANOVA and two sample t-tests are the same. In fact, it can be shown that for two sets of independent and normally distributed random variables, the two procedures are entirely equivalent.
Okay.
Yeah.
Okay.
So,
perfect.
yeah.
Thank you.
So,
Yep.
yeah. Okay. So this is ANOVA and for its relationship with the t-test. And you later you will see the reason why we don't use a t-test. You know, if for example, if we are to compare, let's say three population means, okay, three instead of two. Two we can just use t as just shown here in 10.2 section. But if we have three, then you can say, oh, why don't we just use a t-test how many times? 3 times, right? Mu1, compare mu1 with mu2, and then mu1 with mu3, and then mu2 with mu3. So you just do the t-test 3 times, then you get to know who is different from who. Along with the box plot, you will be not just be able to tell, because the ANOVA only tell you if there is a significant, if at least two of the multiple means are different, at least two of them. But it doesn't tell you the rank, the order. Okay, who is greater, who is the largest mean, who is the smallest mean. So so you need to use it in conjunction along with the box plot. But the thing is, even if you can do that, even if you can use the t-test multiple times, you still have a problem. The problem is that you will have you will inflate the type 1 error, as we can later see in a multiple comparison. So instead of using t-test the multiple time, we either use the ANOVA or multiple comparison, like you will see is named Chefet or Tukey HSD and so forth. Those will be that while you're comparing multiple means pairwise, you control the type 1 error to not be inflated. Excuse me. Okay, so this is a little bit introductory word or a little bit heads up and to define the why we need ANOVA and why we don't use t-test multiple times and so forth. Excuse me. Okay. So now, I like to give you an overview before you get into the, to show it's important. Excuse me. It's more important to show you the forest than get lost in it first. Take a helicopter view and before you get lost in the forest, which the forest, I mean the formula. Sorry. Excuse me. Okay. So in 10.3 and 10.3 and 4, the differences is that one is one factor, one-way ANOVA, and the other one is two-way ANOVA. Okay, method-wise they are the same, but one-way ANOVA, method-wise, I mean randomized. You randomly assign a subject to take a specific treatment. Okay, that's randomized. We call it ANOVA, one-way ANOVA, because one way away is a factor. Okay, but for a factor, it has different levels. So for one-way ANOVA, the levels of that one way, that factor, a factor, consider a factor a variable. So if you have one way, which is one variable, and that variable can take on different values. Of course, in this case, we can have continuous value. You only have different levels. Otherwise, there's no way for you to compare. Okay. So usually we compare like doses, the level, strong, like a strong, medium, and low. The strength of the medicine. Okay, you take the strong medicine or medium or low. Okay, vitamin level high, medium, and low for daily intake, and and so forth. So each level is a treatment. Okay, so that is the one-way ANOVA, and the way that each subject is is to take the let's say vitamin level. You take 3 vitamin a day. You take you take 5 vitamin a day, or some take 2 a day, or some don't take at all. And after a month, observe some bio, measure some bio informations and to see if that make a difference. Okay, so the way subject is assigned to take the test, to take the treatment, is randomized. It's not 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, it's randomized. Okay, and now there's 10.4. For 10.4, the way that subject is assigned to a treatment will be will also be randomized, but now the treatment becomes a combination of the 2 levels from the 2 ways, from the 2 factors. We just said that the way is a factor, is a variable. So 2-way, you have 2 variables and two factors. But each variable, each factor will have different levels. different. Therefore, the different levels, the combination of the different levels from the two variables becomes the treatments. The treatments. And so if in one way you have 3 levels, the other way you have 2 levels, then you have 2 by 3 levels, which is 6 treatments. The combination of the 2 ways is 6. But in this case 10.4, it says the second way is usually referred to as a block block, and it actually makes sense in the real world, and because the other factor, the second factor, usually need to be grouped or be formed into blocks, so that the subjects with the homogeneous characteristics can be grouped together. For example, like colors or races or languages, or yeah, so that you can isolate the influence of a certain for that factor, for that variable. Okay, so then so that your analysis may be more reliable. Okay, so this is a little bit background, and as long as you get the background, then I think you get at least 50% or 60% the content. Because what I emphasize is not that much the formula, because formula-wise, people, it's not easy for you to remember for a very long time. But the concept, it can sink in easily and stay long in your brain. Okay, so we go to 3, 4, and 5. Now, the 3 is here. Okay, completely randomized design. All right. So in this section, we study the hypothesis testing problem of comparing population means. So you can see that what I just said, ANOVA is for comparing means. Although we analyze variance, but our goal is to compare means. And how many means? More than 2. Okay, if there's only 2, as we've seen in the beginning, we could just use T and you get the same result. Actually, they are equivalent. Okay, and so suppose we have K populations, and then each population has sample size. From each population, you draw a sample, and so you have K samples. Each sample has size nk. So sample 1 is n1, sample 2 is n2, and so forth until nk in the subscript. Okay, and you measure the response Yij in the J's experimental unit in the I sample. Okay, so formula-wise, notation-wise, is a little bit strenuous to understand, but not totally impossible. But for people who are not so used to formula, they may be confused. But I think you're okay. All right, so as you can see, what's different, what's make it different from other week is you see the other previously we only see mu1 equal to mu2, and that's it. Here we have mu1 equal to mu2 or to k, and versus the alternative is that not all are equal. That means at least one pair is not equal. Okay. So that's what I said. ANOVA, although it is although it's useful, but the hypothesis test itself is kind of simple. Kind of simple in that it just tell you, okay, I can only say the conclusion you can make is that okay, they are not all equal. But sometimes we want to know more than that, and so that's why you need to go further. You use a box plot in addition, in conjunction with it. All right. Okay, and then or multiple comparison we'll see in the 10.5 section. Okay, so here we see sum of squares. Sum of squares are divided into the sum of SST and SSE. SSC and SSE. Excuse me. So SS is total S. Total is the total sum of squares. Total sum of squares is actually the distances, the sum of the squares of the distances from the mean, of the y. Okay, and that's total sum of squares. Okay, yeah, and that's what it does here. 1 second. Okay, and so forth, and we call it total sum of squares. And but then we have SST is what? Treatments, sum of square treatments, and SSE sum of square error, SSE. Okay, so the treatments address part of the sum of squares. Then of course there are always some errors, and that's their relationship is like this. Okay. Yeah. Okay. So this is their relationship and their formula. You can show and prove that the sum of the two SSE equal to total sum of squares. Yeah. The rationale is that then with that, you see what we are analyzing the variances. Then when we have the variances, then here's the rationale. Are the differences in the means due to the differences? Are they because that the variations among with that's that if you look at this this group, this sample 1, and there's variations within this sample. And if you look at the group 2, okay, also group 3 also. So for these 3 samples, they have their own within the sample variations. But they also GM is a global mean. SM is sample mean 1, 2, 3. Okay, so with respect to each sample mean, excuse me, there is what? There is within the group variation, and with respect to global mean, there is variation. Okay, you see variation of sample mean with respect to global mean. SM1 with respect to GM, SM2 with respect to GM, SM3 with respect to GM. Okay, then here's the strategy. The strategy is to compare the ratio of these two variations. Okay, these 2 variations. Okay, if the ratio is so if let me see. Yeah, You see within group variations, and then among the group variations. Okay, and if the ratio is not too big, then we can say they are not different. The mean is not different. But if the ratio if is too big, then we say, oh, the mean may be significant, right? Mean may be significant. If you see, if the overall mean if the overall mean is variation is not very big, so the ratio as compared with the within group means is not big enough to say that they are different. They are different because they are close. Okay. All right. So and these are the details regarding how you calculate the SSE, which is MSE. Okay, now that we have SSE, SST, and total SS, then we can calculate the mean average. The average is SSE divided by the degree of freedom. Degree of freedom. Okay, and since we have K treatment, then it's m minus 1 minus K minus 1. Okay, so m minus 1 minus K minus 1 is the difference of the 2 degree of freedom, and it ends up m minus K. Okay, and for the other within the group is K, this is mean of the square of tree. The MST is K minus 1, and SST K minus 1. SSE is divided by the remaining degree of freedoms. Okay, so now that you get MSE and MST, and then you calculate the ratio, and that ratio happened to follow the F distribution. Okay, here's the thing. You know, given F, if you recall last semester, you will know that the F distribution is the ratio of 2 ratios. The ratio in the numerator is the ratio is chi-squared divided by its degree of freedom. The ratio in the denominator is another chi-squared divided by its degree of freedom. So the ratio of 2 ratios described just now follows the F distribution. Follows F distribution. Okay. So okay. So this is the foundation of that the ANOVA theoretical background regarding why ANOVA can be used to test for equality of means, as because we used this rationale to compare its means, its variations in this way, and then take the advantages of that ratio of their variances follow F distribution. When this ratio is quite different, you see the ratio is quite different, then its test is statistically big. When it is so big that it exceed the critical value, then we reject. Okay, reject the null hypothesis. Okay, which means there are at least some differences between at least one pair of the multiple means. Okay, so we got to go faster. Like what I said, this is, if you get this basic idea, then I think you got it. Okay, but we need to move on a little bit faster. It's already 30 minutes. Okay, now, so, and the rest of it is similar to, the rest of it is similar to the F test or T test with the, then you can use you compare the test statistic with the critical value, or P, that's called critical value approach, or the of the or the P value with the alpha, and you can that's called critical that's called P value approach. So either approach will give you the same result and same conclusion. Okay. And this is a ANOVA stay. Okay, yeah, we will end in 10 minutes, but I think we need the second session. So whenever it's cut off, let's come back in. Okay. Okay, so you have this ANOVA table summarizing what I just went through, calculating the variability within the group and among the group, and then calculated the average, mean square, MST, MSE, take the ratio, and that ratio follow the F distribution. And so we measure whether within and among are very different. If they are very different, this will be too big or too or yeah, will be too big, and then we will reject. Otherwise, do not reject. Okay. All right. Now, two-way ANOVA. As mentioned, this is called two-way ANOVA or randomized block design. Okay, either way. It has the second way, we also call it block, and there are B blocks of K experimental units each. So in many cases, we may be required to measure response at combinations of levels of two or more factors. Okay, to consider simultaneously. For example, gas mileage, you might be interested in gas mileage per gallon among 4 different makes of cars in both city and highway driving. And that will make sense because each car, the make is different, and so you need to block the car effect, block the car to make them, to put the homogeneous type of car in the same block. All right, and to facilitate your analysis. And also the diet the program among white African American and so forth, because according to a gender. Oh, here is a different diagram per among, according to a gender. So here the second the block is gender, and that also makes sense. Okay. Let me see if it's time and yeah. Okay. So this is a little bit background, and then of course the formation will be a little bit more complicated because but if you follow the same rationale, you will be able excuse me. So you have blocks, okay, and then you have treatments. Then each block, each let me see, each y11 is the is a dependent variable, and so you measure that y given it's in the block 1, and it received treatment 1. Okay. If these are different makes of car, this may be Toyota, Corolla, for example, and it's given different type of gasoline and so you can test. Okay, and this is 2 is Honda Civic, and so forth. Okay, all right. So this is a two-way ANOVA, and but the difference is now is that the total sum of squares become 3 parts. It was just SSE T and SSE. Now you have SSB. So the variation was partitioned into 3 parts, and one is shared by blocks. Okay. So with this, then the formula, the analysis looks is similar. You calculate MSB, MSD, MSE the way you calculate the MSD and MSE in a one-way ANOVA. Okay. And then, and then you calculate the MSB, MSE, MSD, MSE. Okay, and then you compare the MST and MSE. Oh, okay. And then MST and MSB and MSE. Okay. So let's move on. Let's see. 1 second. Okay. All right. So if you to test the null hypothesis that there is no difference in treatment means, you use the MST treatment. T is mean sum of square treatment, and then divide by MSE. Okay. And to test the null hypothesis, there is no mean response for blocks. You use MSB, MSE. Okay. So a test is to test whether there is a difference among different treatments, or different treatments, and the other one is if there's any difference among the blocks. Okay. Of course, although we call it randomized block design, I prefer to call it a two-way ANOVA, because in fact each way is kind of a treatment. It's a variable, okay, and the different levels, the combination of the two different levels of the two different factors constitutes all the treatments. Okay, so and you can see the table become more complicated. Okay. All right. You can follow the formula and then the calculation, but you don't have to go do this composite calculation. You can use R, and so I gave you an assignment for project B. I suggest that you may work on one of the example here which has R hints and tips in R, and to work out the table. Okay, that's not hard at all. It will generate a table for you. Okay, now we have 40 seconds before this section is terminated, because each section is 40 minutes. So after this, come log back in. Okay, we need about probably 10 minutes to wrap it up. Okay. Okay, so this is two-way, right? And I'll leave the rest of it to you. All right, now for the fifth 10.5 section, we talked about multiple comparison. Okay. Okay. Why the reason we mentioned the reason why we need multiple comparison, because I mentioned if you use yeah, theoretically, you can use the multiple t-tests to replace instead in lieu of an ANOVA or but the thing then it will be make the type 1 error much bigger, as you can see here. Okay, here the calculation shows that okay, each time if you if you have four independent four means to compare, and each time you compare two, so for choose two, you have to compare all 6 tests. Now each time you conduct a t-test, you